This is where we'll start today, y'all. All right, y'all, let's go ahead and start with these. So we have a few problems that we want to look at that we're going into our conversation with polynomials. Okay. Whenever we deal with polynomials, there's a few things that we always should start by identifying first. Okay, we looked at that yesterday, and we want to continue with that. So some things that we definitely want to look at is what's the degree of the polynomial we're working with? What is the leading coefficient? All right, and when we look at that leading coefficient, we definitely want to be recognizing if there's a reflection or not. So what's the degree of j of x here? It's 2, right? Now, what word did I use in the directions that would help us know that I meant it to be quadratic? The vertex, right? Once we start talking about the vertex, that's where we're going, hey, this better be quadratic, right? Otherwise, we can't use the word vertex. Now, with that said here, the leading coefficient is -2. So what does that tell me about the graph when it comes to reflection? Is there or is there not one? All right, so since this is negative, right, there is a vertical reflection. Okay, that means when I go draw my graph, it better look something like that. Now, with that said, though, the nice thing about j of x is it's in vertex form. The key to remember there is when I go to state my vertex, what are we also stating? What were the transformations? But that's my shifts, right? So my horizontal shift, I do the opposite. My vertical shift, I do as it says. So I go plot that point right away. Now, based on the reflection, what we talked about yesterday is we know that this is a maximum value. Our graph's going to be below that. Our domain, since it is a polynomial, is all real numbers. But our range here, given the vertex that we just found, is going to be that -infinity to the value of 8. Now, 1 point isn't enough to graph it, right? You can use the transformations to get more points. That's what we've talked about before. So you hopefully can get comfortable with doing that, like knowing that those are solutions there. But what's the solutions I asked us to find? Intercepts. Those are also great solutions to use to help us graph it, right? So let's use those. With that said, let's get this out of the way. And what does finding j of 0 help us get first? That's going to be our y-intercept. That is correct. I definitely recommend using a calculator or something to help you get through that, right? 0 plus 3 is just 3. 3 squared is 9. 9 times -2 is -18. Plus 8 is -10. So guess what? Our next point's going to be somewhere down here. Shouldn't have erased the bottom part of that. The key of our focus here is we found a second point. Now, as we talk about a quadratic and the vertex, right, that helps me as far as getting the range, knowing where this graph turns. Why am I allowed to do this? What am I taking advantage of when I do that? Symmetry, right? This is not an even or odd function, but quadratics have symmetry. This is what we call an axis of symmetry. And that axis of symmetry goes right through the x-coordinate of the vertex. So x equals -3 in this case. So as you see here, these two little points I put here, I didn't highlight it because I'm just kind of using transformation perspective there, is where those 2 points came from. But symmetry shows that they're both 1 away from the axis that we just highlighted. Down here, both of these are 1, 2, 3 away from the axis of symmetry. Okay. Now the next thing we need to get those, not the y-intercept, but the x-intercept, right? Now, what is going to be the key to solving this one? What was it that we need to remember to do? We're setting it equal to 0, and then what should I do after that? This is for any time we're using that standard form of an equation. What are you trying to do when you do it? Yeah, ultimately we're trying to get x by itself, but at the moment we need to get the squared part by itself. Right. By getting the squared part by itself, we can then just use a square root to solve. Yeah. So. Now, should we be surprised here with this statement that we found the -3 plus or minus 2? All right, what's the -3 represent? It's our axis of symmetry, right? Make sure you see that when we do with this, that still it's all centered around that axis of symmetry. With that said, though, we do get two different values, of course, though. That's going to be -1 and -5. Yeah. So I can go plot those out. And we have more than enough to draw our graph at that point. Of course, I did not draw it very well. But one of the things that I want to make sure is clear that a lot with polynomials especially, the sketches are going to be the best thing we need. One thing just kind of highlight as we deal with this, make sure you're seeing here, we're doing a smooth turn. It's not a V shape, it's a curved shape. That's one thing that you need to be careful of with any polynomial. They're curved shapes, not sharp turns, okay? Is there anything I could help clear up here for somebody? Now, keep in mind, as we've kind of talked about this on the test, I can ask for any individual piece, right? I could be like, hey, what is the axis of symmetry? We need to know how to find that. All right, now keep in mind, that's only going to be for the quadratic in this case. That's in standard form, right? Does it completely change then when I get over here, though, in the general form? It doesn't change, right? We just have to handle the vertex part a little bit different, right? Hopefully what you catch on to, though, is that when I go through my list here, the degree of this polynomial is still 2, but we had to look at the leading term rather than the exponent on parentheses. Okay. With that and highlighting that, we now also have our leading coefficient, which is +3, which means no reflection, right? The 3, 2, they do have an impact, stretch, shrink, rise, right? And we should recognize that means there's going to be a stretch, but the main thing we need to take from it is no reflection. When I draw my graph, it's going to look like this, going up, okay? Well, what that also tells me then when I go find my vertex, it's now a minimum. We need to make sure to highlight that, hey, when I go to this next step to get my vertex, it's a minimum value. Now, to find the vertex, though, since it's in general form, we can use that approach we talked about before where we're like, hey, let h equal -b over 2a. You could complete this square. I'm not requiring that, though, okay? Just know how to get to it. With this value here, we'll have negative of -24 all over 2 times 3, which is +4. Now, if that's our x value, the x coordinate of our vertex, how do we get the y value? You have a function, you have an x value. What do you do to get the y value? No. Plug it in. We got to plug it in, right? So make sure you see here, we got to go plug 4 into this, which if we go through that process, what do we get? +1. But that will give us our vertex now of 4, 1. And I can go plot that point right away. Now make sure you see here, that's our minimum value, right? So what am I not going to cross right now? I'm not going to cross the x-axis. Everyone see that we're not going to have anything down here as far as our graph is concerned? That goes back to recognizing if you have a reflection or not. If you wanted to, you can go graph this just using transformations. What? All right, just make sure you see there how far up did I go for these next points from here to here? How far up is that? Just 3, right? Where in the world did I get the 3? The leading coefficient, right? 1 squared is 1. That's the nice thing about, 1. It works out nicely off time. So 1 times 3, hey, look, let's go up 3. Now, with that said, though, let's make sure we put confirmation in that because we still need to define our intercepts. So if I try g of 0, right, what we're going to see here is that would give us positive 49. Well, that's going to be way out here somewhere off my screen. Okay, so that is definitely going up as far as the y-intercept is concerned. Okay, so we're not going to worry about plotting that. But when we go deal with g of x equal to 0, what are we going to run into probably? What type of solutions will we get if we do not have x-intercepts? Which hopefully from this piece here, you're already saying no x-intercepts. But remember here, for one, we shouldn't be able to factor. Okay, we definitely aren't going to get rational factors here, so we shouldn't be able to use the A times C method because 3 times 49 is not going to turn out nice. And then any way you combine 3 and 7 times 7, you're never going to get 24. So we have to be careful there, right? With that said, also remember, as I stated yesterday, if you choose to use the quadratic formula, focus on this piece first. That's inside the square root. Okay, so if we focus on that alone, we'll have negative 24 squared minus 4 times 3 is 49. Now, what type of number am I about to get from this? A negative, right? We should be expecting a negative number here. Is that clear to everyone? And lo and behold, we get negative 12. This here confirms that we do not have x-intercepts. It's in agreement with what we see up there. This is one of those places where you can do all the work to find it, which I would hope we're able to do when it comes to finding intercepts, do all that work and just show, hey, I have an I, no x-intercept, or you can go and then write out to me why you don't have an x-intercept. Does everyone see that? You could simply say to me that, hey, my range here is 1 to infinity, and 0 is not included in this range. That's a great way to go then state no x-intercept. If 0 is not in my range, I can't have an x-intercept. Does everyone follow that? Now, keep in mind, as we shared before, too, if you choose to do the quadratic form, the complete and square approach, you're going to find that, hey, I'm going to get a negative in my square root, right? So I'm going to have to put I, and that's the other perspective. I don't want imaginary numbers. I wanted real numbers, so there's no real x-intercept here, okay? Any questions with this one I can clear up? All right, so what changes with this one? What's going on here that definitely changes the perspective of what we've been doing just now? There's 4 terms. Why is there a 4th term? What do we have? What should I highlight when I look at that? I think both of those would probably be good terms to highlight, right? First and foremost, x cubed is our leading term, right? We like the leading term because from there, we can start kind of sketching stuff out, right? So it wanted me to identify the degree of this. So from that leading term, hopefully you're seeing the degree is 3. So this is a degree 3 polynomial. All right. Well, from the leading term, we should be able to get the leading coefficient. So since we know that, we should see also that that leading coefficient is 1. All right. Now, make sure you kind of note to yourself, no reflection. That would be one thing that I think is good to kind of keep an eye on. And we're going to talk about that a little bit more as we go through this problem. Okay. Now, before we go into the end behavior, which is going to have a lot to do with the reflection, how many turns will this graph have at most? Right. At most 2, right? That there's no more. So make sure you see here that the max number of terms, the max turns is going to be 2. We got that by taking the degree and subtracting 1. That's going to be the same thing. Right? You want to know the max number of terms? What's the degree? Subtract 1. Hopefully you're catching on. The degree of a polynomial helps me out a lot. We started with, from equation standpoint, that when I see a degree 3 polynomial, I should expect 3 solutions anytime I have an equation. We've added to that, of course, as we just saw on this one, that sometimes our solutions might be complex, right? So they're not always x-intercepts. Make sure you keep that in mind. We can run into complex numbers and polynomials all the time. So please remember as you deal with that, that you might run into something that has 3 solutions, but you can't graph on it. Okay. The next step to that is dealing with the maximum number of turns, right? We're adding this to that layer now to say, hey, not only does this help me know kind of a basic idea of far as solutions, it can start helping describe the shape of the graph to me. When I think of x cubed, we started with this shape here, and now we're kind of expanding it to this more S-shaped situation. Okay. And anytime we have a reflection, we just take that same shape and flip it over, right? So keep in mind that would be, you know, the situation of a reflection. Right now, we don't have a reflection, so we don't need to worry about those. But we know that's what our graph should look like in general. And we're going to use that moving forward. Okay. Now, with that said, we could talk a little bit more about the end behavior because that'll kind of give me the idea of what's going on with this. Now, the way we want to write the end behavior is as I go to my graph here, I'll just pull in a quick as we go to our graph, end behavior saying what's going on to the far left end or to the far right end of this graph. Intercepts would be kind of what's going on in between. That's what we look at. But on the extreme edges of the graph, just kind of in quick general, what's going on, right? Now, make sure you have that graph in mind, though, because as I just said, it should look something like this. And behavior says, don't worry about these middle pieces, just worry about these end pieces. Okay. So the way that we could write that then is to say, hey, as x goes to negative infinity, or the left-hand side of our graph, what is f of x going to do? Based on how I've drawn this piece here, does that mean it's going to go down or is it going up as I go to the left? It's going down, right? We could say something like, hey, it falls. Now, another way to write that would be to say, hey, it goes towards negative infinity. Okay, so make sure you see this notation because that's definitely something you see on the assignments. But also make sure you take it to that, like that just means left-hand side of my graph. And that means they're going downwards, or what we're going to say is falling. We don't want to use the word decrease here because that's reserved for a rate of change. Okay, so that's why we'll use rise and fall. Now, in the same way, then, we can go over to the other side and say, hey, the right-hand side of my graph is going to positive infinity. What is f of x going to do there? Is this going up or going down as we go to the right? It's going up, right? And so you'll see there, we'll say positive infinity, and that's where we'll use the word rise. Okay. This will be a situation where, if, like on the test, I ask you for end behavior, you can just make a quick chart that says, hey, this is my left hand, this is my right hand. I'm perfectly fine with you saying fall, rise. However, we also need to know that there's a mathematical way to write that. And that's why I feel the homework's going to come in and make sure we get practice with that. Okay. Any questions where I'm coming from with those statements? Now, make sure you see here the two sides. Are they doing the same thing? They're different, right? How could we know they were different from the beginning? Not the negative. The degree, right? Anytime the degree is odd, you should see different behavior. So this right here, the fact that these two are different can be seen by the fact that, hey, we were dealing with an odd polynomial when it comes to the degrees. All right, not odd in the sense of symmetry, but just, hey, 3 is an odd number, right? If you had x squared, well, guess what? The two ends do exactly the same thing on both sides, right? We say both of them rise going up to infinity, okay? Now, with that said, though, that's not all we wanted to do here. We also need to do the intercepts. Are we good if I put f of 0 equals -8? Hence why I highlighted the -8 from the beginning, right? Just to make sure to say, hey, that should be something we're catching right off the bat. If I have a constant term, that's my intercept. If I don't have a constant term, that means the origin is the y-intercept. The next step then is to set the whole function equal to 0. What would someone do with this function? Now, as I've stated before, is grouping always going to work? All right, this is one thing that I've said the last 3 or 4 days now, right? Grouping doesn't always work, but that's definitely something we want to try. So if we pulled out our greatest common factor from the first two, and then do the same thing with the second two, we find that, hey, grouping does indeed work here. And we can go a couple more steps, actually, because when I factor out x plus 2, x squared minus 4 is a difference of squares. Okay? So we could say x plus 2, x plus 2, x minus 2, all equal to 0. How many solutions does that give me? It's 2 solutions, right? X equals to -2 and 2. But remember, that's where we're going to use the word multiplicity, right? The multiplicity of both of these is, hey, -2 occurs twice where the +2 occurs one time. All right. And this is where we're seeing that these two are exactly the same down here. So make sure we keep that in mind. So I found 2 solutions, but because of multiplicity, it does still agree with the degrees of 3. Any questions there? Now, why do we do all this? Well, we did all this to graph it. All right, so make sure you see here, I just brought all this over. I should copy this as well, though, so let's bring this over. Now, as we deal with this, all this information is going to help us build a graph, okay? The points that we have already are going to be our intercepts. So make sure the first things that you're doing is plotting your intercepts, okay? Now, when it goes to draw this too, why am I putting this? Where did I get those little line segments from? Then behavior, right? Now, is that going to be perfect to what it should look like? Absolutely not, right? What you're going to find here is that when I go to do this, all I can really do is sketch it as best as I can, all right? However, the key components here are going to be in behavior and the solutions. On top of that, we have to look at multiplicity, right? So to start with the easier side of things here, we can focus on what's going on with x minus 2. Now, x minus 2 means that's our focus there with the +2 x-intercept. How many of those factors do we have? Just one, right? So that treats it like anything we've dealt with before, where we're going to take our graph and say, hey, I just got to cross straight through this and continue upward from there. So I don't need this little guessing. Now, what's going to happen, hopefully you see, is I got to go downwards and then back upwards. So there's going to be actually one of my turns. And I know I have to go back upwards because guess what we have here? Another x-intercept, right? So we come over here and highlight the fact that we have this x-intercept as well that we need to deal with. So as I do that, I'm going to draw my graph so that it goes down and then back up to this other x-intercept. Now, what's the issue we run into here? As we approach this x-intercept and we know that we need to be over here, what must happen? I have to have another turn. Does everyone understand that? Now, if you treat all x-intercepts the same, you're like, oh, just cross through and turn back down. What do you create in that process? All right, this is something that we need to talk about. And this is where we're going to start talking about how multiplicity is very important. How many x-intercepts should we have? All right, we did the work to show that I should only have 2 x-intercepts. Right? But a common error I see students make is when they go in here, they're like, okay, pass through this, and I got to get back down. Well, when you do that, you just created a third x-intercept, and we do not want 3 x-intercepts. So we cannot do that. So what we see here instead is this is where our multiplicity comes in. All right? So if I kind of step back from all that, whenever I'm dealing with this, I always start by kind of drawing my end behavior, and then I focus on multiplicity of the zeros. So for instance, since x minus 2 only occurs once, when I zoom in really close to this, I should be kind of seeing a linear pattern. It's not linear, but the pattern around that as we zoom in on that x-intercept is going to be similar to a linear pattern. With that said, over here, how many times does this one occur? Right? It occurs twice. That's going to be more like a quadratic pattern. So what you'll see is instead of crossing here, it's actually going to bounce at that particular point. We actually know one of our turning points is what that means. It's not a vertex, but it is similar to a vertex. And that, hey, that is the turning point that we're dealing with on this graph. Now, with that, I can then zoom back out and say, hey, I can connect all of this now and say, from this intercept, I could just continue downwards. From this intercept, I can just continue upwards. In between, I need to go down to my y-intercept and then turn up. Just make sure you remember your turns need to be smooth, not these. Okay. Now, do we know where this occurred at? Or this turn occurs at? Have we talked about knowing exactly where a turn occurs other than the vertex yet? No, and what you're going to find is this would go back to the difference quotient, and it's not something that we can handle from our perspective right now. We need more mathematics to be able to describe that. So know that when you draw this, if you just went down here and did that, technically it's not far off. That clear to everyone? So know that I'm not looking for perfection. Things that I'm going to check for. Are we agreeing with what our end behavior should be? Okay. The second thing, do we have our x-intercepts in the correct place? And are we using the correct number of x-intercepts? And then when I look at that, did we treat the x-intercept behavior correctly? So as you see here, I bounced off of it, forming like a micro x squared in that one area. Or again, over here, I crossed straight through because it only occurred one time. So I treat it kind of like a linear in a sense. Lastly, though, is don't forget your y-intercept, right? That's why I went that far down to begin with, was the y-intercept. Okay. Questions, concerns here I could clear up as far as talking about this function f of x, right? Going through the process of finding everything and then using that information to help us graph. Right now, then over the next several days, know that we're going to be kind of adding to this, right? Because one of the issues that we're going to run into is what happens when I can't factor it, right? So that's one perspective that we have to be prepared for. This is me just making sure to introduce to you kind of what some of the things that's changing, all right? So what if I gave us this one and I just said, let's walk through sketching the graph of this function. Let's see how that looks through this process. So hopefully we're going through a couple patterns right now, right? What's the first thing someone's writing down after they write the function? Yeah, hopefully we're writing the degree. What were you going to say? All right, well, before we get to turning points, right, make sure we state that the degree is 5, which definitely means the max number of turns is as you mentioned, 4. All right, the leading coefficient is 1. So from there, you're saying we could do in behavior?
Yeah, like the left hand side, and it falls. The right hand side, it rises.
So does everyone agree that this is going to be similar to the cube with more turns, though? It's x to the 5th is an odd power, right? So we should see similarities there. Now, there is one thing I want to add to this, though, before we go forward, right? As we begin to work with polynomials and you're going to graph them, and that your objective here is to graph them. Keep in mind, my previous one, I didn't say graph. I took that as an extra step. Let's check the function to see if there's any symmetry involved. Because if there's symmetry involved, that's going to help us graph this even better, right? And the way that we check for symmetry is plug in what? Negative x, right? So take your function, and this isn't, something that's often required, but it definitely helps the process of graphing. Now, the reason I'm saying that, what is both the exponents on those terms?
Odd.
They're both odd, right? So there's kind of one of those things where, hey, I possibly might have some symmetry here. Let's go see. Make sure you're careful with that, though, because as we work through this, watching your signs here, if you have 5 negatives, the result's going to be negative. 3 negatives, the result is negative. We do not get the same function back, so that's why we go one more step to say, hey, this is equal to the negative of our function. So if I pull a negative, I'll get the positive x to the 5th and the negative 9x cubed again. So if you need to see it, just write it out where it's like, hey, if I pull out a negative, change my signs again, and then I'm back to where I started. Because of that, we can conclude that therefore G is odd. Why is this helpful? Well, that means if I go over here and plot the point 2, 3, then negative 2, negative 3 is also a solution. I only have to focus on one side of my graph now and get the points I need and copy it over to the other side. But be careful, odd symmetry is through the origin. Same value, but opposite sign. So be careful with that. But that's definitely something that's going to help us kind of with the graph. Now, did I tell us to do that here? Is that a requirement? Did I tell us to do that on the previous problem? No. Now, why would I encourage you not to do it on this one? What do we notice about the exponents here? One's even to one odd, right? We're just looking at 3 and 2. At that point, hey, I probably don't have symmetry, so let me just move on, right? Whereas here, they were both odd. That might be why it's worth your time. Okay. With that said, though, I feel like we have a good general idea of kind of what our graph's going to look like. If I go to graph it, I can do something kind of just a sketch that looks like this. Probably something along those lines. The reason I feel like that is just because, hey, we got to have the in behavior in place, but it's also got to be symmetrical. So there's got to be something going on with that origin in general, right? But that's where we should go find what next to ensure that we have all that correct information. That's where the intercepts come in, right? So if we plug in 0, we're going to get 0. So we can definitely have confidence that that origin is a solution for this function. Right? Again, there's no constant term here. That's what even made me want to go look at this. Okay. The next step, though, is to find the x-intercepts. Well, what is someone going to do with this when they try to find the x-intercepts? Oops. How do we go about solving this? What's going on with the two terms that we need to recognize that they have in common? And they have x's in common, right? Specifically 3 of them. So we need to factor that out as a GCF. Once I factor that out, okay, the GCF is done. We're good there. So we have one of our zeros. Well, we need to factor this out. Now, you could use the square root property. I understand that if you prefer the square root property, but we also need to be comfortable with factoring. You're going to have problems that ask you to factor this, so you need to know how to factor this one and the sum or difference of cubes. You need to remember both of those. They will come up. With that in place, though, that allows us to show that, hey, 0 is an x-intercept, -3 is an x-intercept, and +3 is an x-intercept. Okay? What is special about one of those, though, we have to be careful with? How many x-intercepts did we just find? 3. What was the degree? 5. Does 3 agree with 5? No, we have to go talk about multiplicity, right? So make sure as you look at this that you're saying, hey, once I find my zeros, let me get in the habit of saying, hey, let's check to see if there's any multiplicity. Because over here, what we're going to find is 0 occurred 3 times, where these others occurred only 1 time. That's where we'll see, hey, 3 + 1 + 1, that's now in agreement with the 5 that I should have had. Okay. Now, with that in place, though, we can plot -3 and +3 as our x-intercepts. The other aspect here then is to start kind of talking about how the multiplicity affects our graph. Make sure you remember in behavior, though, we did state that it should look something like this. We got to go kind of fill in the turns, though, is what we're doing now. So -3 only occurred 1 time, so I'm going to draw kind of a line through that. It's not going to be a perfect line. We're just doing a sketch. We need more points to get more accurate. I'm going to do the same thing over here with that +3. And what you're going to see is that from the 3, I'm going to go up. From -3, I'm going to go down. But we have to do some turning here to get to the origin, right? Now, I'm going to do my best to make these turns look similar. But one thing you have to understand is when we talk about the origin, why am I drawing it this way? It's cubed, right? It was x cubed when we looked at multiplicity. Let me change this color. Right? So as you saw over here with these two, they only occurred once, so I went straight through them. Cross them is the most important part, okay? As we did with this one, though, I want to show that it flattens out a little bit as I go through. But if we zoom in there, you might have thought, you would hope that you can look at this, and this is what I'm hoping you take from this, is that if we look at that, that looks like x cubed almost, from just x cubed by itself. The difference is I got to zoom out because there's more going on here than just that one piece of the graph, right? We need to use that to say, hey, I got a curve here and curve here to finish my graph out. Now, my graph's not going to be perfect again because all we're doing is a sketch. All right, we would need to have more stuff to get a better graph than this. But as far as us, and what we're concerned, these are definitely some things that I'm gonna be looking for is that, hey, did we properly cross through here those intercepts? A next step would be, hey, did we show something like this where it flattens out a little bit because it was cubed rather than just an exponent of 1, right? Those will be some other things that we focus on. As far as today is concerned, I would make sure that we're highlighting that, hey, the degree was 5, and we talk about max number of turns being 4, but here really we only had 2 turns, right? Because a lot of that had to do with this being x cubed. All right. As we also deal with that, make sure we're getting comfortable with this idea of end behavior, right? We can know from the beginning what's going on in the extreme edges of our graph. That doesn't mean we're going to have specific ordered pairs, but we do have information as far as like, hey, is it going to fall or rise when I go to graph this, or if I look at the graph? Okay. Any questions there? All right. The only thing different you'll find is I can put it in factored form for you on the test. So make sure you're comfortable with that. And that was where we looked at that one yesterday. Where did I put it? Like this one here. Make sure you're comfortable with that idea, just being prepared to read in a factored form. Okay. But if you don't have any questions, have a good day, and I will see y'all tomorrow.